Okay, Mr. Nagy's Physics 11 class. Moving on with our kinematics unit. We're talking about acceleration now. The first thing we did in the acceleration unit was simply a ticker timer type activity, and we wanted to look at different graphs and so on. So really quickly, when we took and attached our ticker tape, oh, not my best drawing, but what was happening was the dots were getting further apart each time interval. Uniformly, I hope. We spent some time talking about positive and negative directions and so on. Did a few activities having to do with that. So we're moving on now and looking at a fairly, hopefully, intuitive case. We did use acceleration to cause our accelerated motion with the ticker timer activity. And now in class what we're doing here is we're going to throw a ball up in the air like this girl over here is doing. Throw it up in the air. We're considering the motion of the ball after it leaves her hand. Obviously gravity is going to act on this, and gravity, I think we can all say, is going to act in a downwards direction. It gets to the top, and it says here the velocity is 0 right at the top for an instant. And we've been using the word instantaneous. Instant, I need an S in there. We're going to use that word a fair bit. It's hard to define exactly how long this ball stays with a velocity of 0 at the top. We're going to use the word for an instant, or it stops instantly. Anyway, it's a really small portion of time, but it does stop at the top, then it accelerates. Now this little diagram here shows all kinds of stuff. We're really considering it to the same distance. The activity we did with our motion detector, we put it at the top of a ramp like this. We gave a ball a push, and it rolled up and then turned around and came back down. You can see the turnaround point there. These little diagrams here are as if it were a strobe photograph or perhaps attached to a ticker timer. We weren't able to do that. Anyway, what did the graphs look like in this particular instance? So when we graph these things out, and I'm going to throw a graph on here, and this graph's a little tricky because I've got 3 different graphs at the same time. In yellow is our displacement time graph, okay? There's our displacement axis over there, and then they put velocity and acceleration over here. So your displacement, at the moment it leaves, it's 0 from the girl's hand right here. Okay, so you're starting right there. And a few moments later, you're up here. Time is going along here. Quite a long time axis in seconds, but they would be the same shape graphs that we saw with our Logger Pro on our screen. It gave us 3 graphs, one above the other, and here they're superimposed. So it's an inverted parabola like this. The tricky part here is notice that we've got a 0 point on our velocity and acceleration time graphs over here, 0, right? And the red here is our velocity, and the yellow was our displacement, how far it's gone. So the velocity starting up right here, it's got a fairly large velocity as it left her hand. She threw the thing up, and a moment later, right, the velocity is a little less, and then it's less. I guess we're reading on this axis. So it's slowing down on the way up. If I wanted to draw little velocity vectors, got a long velocity vector there. This point here, it's a little less. At this point here, I've only got a little bit of an upward velocity. And again, it's 0 at the top. And then, there's our 0 point again. Down here, our velocity becomes negative. At this point, it would have basically the same velocity as it had there. So if I'm a fraction of a second before, the same distance or the same time after it stopped, and this where velocity is equal to 0, right there, I've got the same velocity only on the negative side, right? At the same time, I've got the same velocity. And right here, it's going that, and then down here at the bottom, when it gets back to her hand, it's going the same as it was, only in the negative direction. Remember, we're saying by convention, up is positive and down is negative. Now, what about the acceleration graph? And this is where we probably hit a surprise when we had our acceleration graph on our motion detector. Our acceleration graph in blue here was 0 the whole time, or 0 was a negative value the whole time. It never hit 0. Pardon my wording there, right? Acceleration is constant, okay? And by constant, right here where the velocity is 0, that's right up here, my acceleration didn't take a dive up, so to speak, to the 0 mark. If it were at some negative value the whole time and 0 there, it didn't, whoops, go up. It didn't make a point. It never went up to 0. The acceleration was always the same value. And why not? Did gravity change on the way up or down? No, gravity is the same, and gravity is what's causing that acceleration. We really do expect the acceleration to be uniform. So a key thing there on recognizing what these graphs look like for an object that's going kind of up and then down, thrown up and throw down. Okay, now, next thing we're going to do here on this video is consider what we've been analyzing in terms of kinematics, the variables. We're going to derive the formulas that are at the front of Mr. Nagy's class. Variables for uniformly accelerated motion. Well, we might be talking about where an object is, the displacement. We're concerned with the acceleration. We're concerned with how long it's undergoing the acceleration. And we're probably concerned with initial velocity and final velocity. Again, the subscripts are just to help us identify the two things. So up here, there's our acceleration, our displacement in the green there, time along this axis right here, and initial velocity and final velocity are all things we want to consider if it's changing for whatever interval we're watching an object for. Okay. We have figured out from our studies of uniform motion that velocity is equal to displacement over time. I'm leaving my little deltas out of there. And acceleration is velocity over time. Okay, and again, I'm being kind of lazy here, but really each of these is involving a change in. Acceleration is a change in velocity that occurs in some time. And a change is always the final value minus the initial value, right? Delta means final minus initial. So it's V final minus V initial in this case. So acceleration is VF minus VI over T. Now I can rearrange this thing. Sometimes you may want to know VF. So I'm going to take the T up there, and A times T is equal to VF minus VI. And the way we've got it written at the front of the class, I'm just going to add VI to both sides. VI added it there. We've got written at the front of the class, VF is equal to VI plus AT. Okay, that's the first equation that we've got written in the front of the class, and it's really just a manipulation of this equation right here. Now, your average velocity is your total displacement, and I'm going to put some subscripts here. D total, this goes back to the uniform motion. We said, consistently talked about our trip to Penticton thing. But let's take a look at this graph here. Here's a uniformly changing velocity. The average velocity, provided it's uniformly changing, can always be given by, it's going to be halfway in between. The average velocity is equal to the initial velocity plus the final velocity divided by 2. Scoot back to the graph right up here. There's the final velocity, or the initial velocity. There's the final velocity for the object thrown up and coming back down. And the average velocity is always going to be right in the middle as long as it's uniform. Okay, so just putting that in there, I'm going to rearrange this. I'm going to put D total, when an object is uniformly accelerating, is equal to V average times T, and V average is VI plus VF over 2 times T. Okay, I'm going to leave that little subscript off. So there's another equation that I've got at the front of my room for uniformly accelerated motion. Okay, D is equal to VI plus VF over 2 times T. and VF is equal to VI plus AT. So at the front of my room, that's the second equation on the board. At the front of my room, on little pieces of yellow, that's the first equation we've got up there. Now, notice that this one involves four variables, right? D, VI, VF, and T. And this one here involves four variables. I'll put those in yellow, VF, VI, A, and T. So out of our 5 initial variables here, each one involved 4, but not necessarily the same 4. There was a second one, and the first one involved that, and that. It didn't involve acceleration, okay? And the second equation didn't involve D. Now, let's just kind of pre-do some algebra here. Let's substitute VF here into this equation. We're just substituting equations right there. So let's say we didn't know VF, but we kind of knew this equation for it. So D is equal to VI plus all of that. VF plus AT all over 2 times T. Whoops, this was VI plus AT. Okay, so D is equal to VI plus VI is 2VI plus AT all over 2 times T. Okay, and let me just put some brackets around here and do the old feed the chickens. So D is equal to 2VI T plus AT T, and that would be AT squared all over 2. Just simplifying to make it a little bit neater here. 2 being a common factor, so watch, I'm going to put 2 under there and 2 under there, a common denominator, pardon me, and here it'll divide out. So I get D is equal to VIT plus AT squared, because T times T is T squared over 2, and we often can write that as 1/2. Dividing by 2 is the same as multiplying by 1/2. So D is equal to VIT plus 1/2 AT squared, and that's the next equation we've got at the front of the room. That's the third equation. And lastly, and really, or T. Let's say we don't know T. So I'm going to go VF minus VI is equal to AT. So T is equal to VF minus VI over A. Just doing some algebra here. I'm going to substitute that, and I'll do this in gray, that in for T. Okay, so back to this equation up here, I'm going to have D is equal to VI plus VF over 2. I'll put that in brackets, and T is equal to that, VF minus VI over A. Now, denominator times denominator will stay on the bottom, 2A. On top, I've got sort of binomials, I think they call them in math class, so I need to use FOIL to figure those out. So VI times VF is VI VF, VI VF, and then, so that's first, and then outside is minus VI times minus VI, so minus VI squared, and then inside is VF times VF, so plus VF squared, and then last is VF times VI, but it's a minus this time, VF VI, and VI VF minus VF VI, that's the same. So ultimately I get here D is equal to, I'm just going to rearrange these a little bit. I'm going to write VF squared first, minus VI squared, it's a little bit easier, over 2A. And I'm going to take that up, a little cross multiplying. VF squared equals VI squared plus 2AD. Okay, and that is the fourth equation that we've got at the front of the room. Our 4 basic kinematics equations that we can use, and really they're simply derivations from looking at the graphs of uniform motion involving the different variables. They all start from this equation and this equation. We've done some algebraic derivation here. They're not some magic formula, and in the next video we're going to look at how to use the equations.